Welcome everybody for the last day, and I'm pleased to introduce Takayuki Kihara, who will speak on Weihrauch reducibility on multi-represented spaces.
Thank you very much for the introduction, and thank you very much for inviting me. So today I'd like to talk about the Weihrauch reducibility on multi-represented spaces. So the notion of Weihrauch reducibility is, I think, one of the most important concepts in recent computable analysis. So basically used to classify such problems or mathematical theorems. So yeah, it can also be interpreted as giving a computability-theoretic classification of mathematical theorems. However, Weihrauch reducibility is a notion usually defined for functions on represented spaces. This time we are going to extend it to multi-represented spaces. Okay, so the notion of so I'd like to introduce the notion of multi-represented space, which has been studied by several people. So the notion of computability is usually defined for natural numbers or bare space, but when we often want to consider computability for ordinary mathematical objects, so in such cases, we use represented spaces. So I think all of you are familiar with represented spaces, I think. So the idea is that we can use natural numbers or sequence of natural numbers to represent other mathematical objects. So a represented space is a pair of a set and a partial surjection. And so yeah, basically, so if we write delta xp is equal to x, then this means that p is a name of x or p is a code of x or something like this. But now, so in this talk, we want to consider a multi-represented space. So this is a pair of a set and a surjective relation. So this means that, well, maybe, so yeah, it's equivalent to say, so a surjective relation is the same as a surjective multifunction. So yeah, basically, so yeah, some multivariate version of partial surjection. So, and if so, but we use the relation symbol like this. Maybe it's yeah, this notation may be useful. So and so if we write p, yeah, something x, then this means that p is the name of x. But in the case of a multi-represented space, so one name can represent many points. So one p can name many x. So yeah, so yeah, but the idea is almost the same. So in the case of a represented space, so one name can only represent one object, but and a single name indicates a single point or something. But in the case of a multi-represented space, a single name may may indicate many things, many points. So yeah, so in the context of computable analysis, it is called a multi-represented space. But so this notion is also used in other areas like realizability theory. So in the context of realizability theory, it is also called an assembly. Okay, anyway, so to take a concrete example of a multi-represented space, so for example, the standard way to represent a second countable space is to use a neighborhood base. So and if so, I don't explain the detail, but if it is a T0 space, then the points are uniquely determined by from their neighborhood bases. In other words, so this is a usual represented space. On the other hand, if the space is not T0, then the points are not uniquely determined from their neighborhood bases. So it is only a multi-represented space. So from a topological point of view, one of the advantages of considering multi-represented spaces is that we can also deal with spaces that are not T0. Okay, so there are several people who have thought about Weihrauch reduction on multi-represented spaces. And the first one was probably Andre Bauer. His paper was published in 2021, but he seems to have been talking about the idea for more than 5 years. But he so he called this version of Weihrauch reducibility the extended Weihrauch reducibility. And as a different person, Matthias Schroeder independently introduced more explicitly two types of Weihrauch reducibility on multi-represented spaces. So there are a total of three definitions of Weihrauch reducibility on multi-represented spaces so far. So, well, for now, let's start with the original definition of Weihrauch reducibility. So this is first I introduced the usual Weihrauch reducibility for Bayer space. So this is a usual definition of Weihrauch reducibility. So the Weihrauch reducibility between multi-valued function on Bayer space. So a multi-valued function on Bayer space, in the case of Bayer space, so the definition is relatively simple. So yeah, so it's a usual definition. So I read it. So a function f is Weihrauch reducible to G if there exist a partial continuous, partial computable functions, phi minus and phi plus. So phi minus is inner reduction and phi plus is outer reduction. So it is, yeah, they are often written as HK or something like this. So there are such phi minus and phi plus such that given an instance of f, of the given x in the domain of f, so the inner reduction phi minus yields some element in the domain of G, so something like this. And then, so given a solution of G x tilde y, the outer reduction is a solution of f of x, so something like this. So, okay, so I will explain this this figure. So for later use, it's useful to understand this definition as a game. So this is a game description of Weihrauch reducibility. So in this game, there are two players. I call opponent and proponent. Okay, so first, opponent chooses an input for x. In response, a proponent makes a query that is chooses an input x tilde for G. Then opponent chooses a solution y of G of tilde x. And the proponent looks at it and makes a solution y tilde of f of x. So this is a Weihrauch reduction. The important point is that the proponent's first move depends only on x, and the next move depends on x and y, since the game has more information in later rounds. So this is a Weihrauch reducibility in the case of Bayer space. But next, let's consider Weihrauch reducibility in the case of a represented space in general. So this is the definition of Weihrauch reducibility for any represented spaces. So it is necessary to explicitly use names of points in the discussion. So, okay, so assume that x, y, x prime, y prime are represented spaces. Then, okay, so consider a multi-valued function on the represented spaces. So f is Weihrauch reducible to G means that partial computable functions phi minus and phi plus on Bayer space, such that given a name green x of input blue x of f, so the inner reduction phi minus is a name, so name of some input of G. So phi minus is the name of some x tilde in the domain of G. Then give a name of a solution of G tilde x. So green y is a name of blue y, which is a solution to G tilde x. The outer reduction is a name phi plus xy, which is a name of some solution y tilde of f of x. Okay, so this is a usual definition of Weihrauch reducibility for usual represented space. So, but we use this symbol to extend this definition to multi-represented space. Okay, so to illustrate this definition using a game, so this definition is like this. So first opponent provides a name of an input x of f. And in response, proponent makes a query for a query by seeing the name green x, then gives a name of an input x tilde of g. Then opponent presents a name of a solution y of g tilde x, and the proponent looks at it and makes a name for a solution of f of x. Okay, so it's the same process as before, except that it involves names. In this game, opponent and the proponent use only names to discuss, but in the case of represented spaces, the points are uniquely determined by names. So there's no ambiguity in discussing only by names. However, this argument does not hold true in a multi-represented space. In a multi-represented space, a point is not uniquely determined by its name, so it must be considered carefully. Okay, so this is a game from the previous slide. So the problem is that x tilde is not determined from pros phi minus x. So, and this answer y by the opponent to the query depends on the solution of g of x tilde. So I mean this part must depend on x tilde. But x tilde is not determined by phi minus x. So this is a problem. So the information of x tilde must be explicitly given. So so when a proponent specifies the name phi minus x, the point x tilde is also explicitly chosen by proponent, and the same is true for y tilde. So in other words, so in the case of a multi-represented space, proponent will provide not only a function phi, but also a function gamma to select a point at the same time. So this gamma are used to select x tilde and y tilde. So the right description of Weihrauch reducibility on multi-represented spaces is like this. So proponent also have other two functions, gamma minus and gamma plus, and this is used to choose points here. But yeah, this is basically the only part that changes. So opponent first creates a point input of f and its name, and proponent creates both an input of g and its name. In response, opponent creates a solution of g something and its name, and then proponent uses this to create a solution of fx and its name. So this is the idea of defining Weihrauch reducibility on multi-represented spaces. Okay, so the formal definition might look something like this. Okay, so let x prime, y prime be multi-represented spaces, and consider multi-valued functions on multi-represented spaces. So a multi-valued function f is Weihrauch reducible to g if there exist partial computable functions phi minus, phi plus on Bell space, and partial functions gamma minus and gamma plus, which are not necessarily computable, such that given a name of any instance, so any input x for f, so phi ex is a name of input for g, and so phi minus x is a name of input gamma minus green x, blue x of g, and then give a name green y of any solution, blue y of g of tilde x, phi plus xy is the name of some solution, gamma plus green x, blue y of f of x. So I use green symbols to represent green symbol to mean names and blue symbols to mean points. Yeah. So, okay, so in the case of a multi-represented space, the process of selecting a point as well as the process of selecting a name is given by a proponent, since the point is not determined simply by name. So, however, the notion of computability is defined only on the name side. So the name selection process requires computability, but the point selection process does not. Okay, so as a matter of fact, there are many variations on how to handle this part. And for this reason, several variations on the definition of Weihrauch reducibility on multi-represented spaces are proposed. So this definition is the same as Andre Bauer's definition, but different from Matthias Schroeder's two definitions. So there are three definitions. So this is the first definition of Weihrauch reducibility on multi-represented spaces. Okay, but I mainly use this definition in this talk. Anyway, so now, okay, so this is the same game as in the previous slides. So now in the case of Weihrauch reducibility on multi-represented spaces, the definition involves four functions: phi minus, phi plus, gamma minus, and gamma plus. So, so the definition is quite complicated, and it is not so easy to remember the definition because it's a lot of symbols, phi plus, phi minus, yeah, gamma plus x, x, y, y. Yeah, it's quite complicated. So, so it's a little difficult to read because of the many parameters. So let's write it simply without phi and gamma explicitly. So opponent first creates an input of f and its name. And proponent creates both an input of g and its name as a query. In response, opponent creates a solution to the query and its name. And proponent uses this to create a solution of fx and its name. And so, for example, this x tilde depends on this green x, and this no, I need gamma in my definition. I mean, so this is a multi-represented space, so a name does not determine a single point. So phi x may be a name for many points. So for example, so phi minus x is, so I mean, if it is a represented space, we don't need gamma, but if it is a multi-represented space, one name can represent many points. So phi minus x does not determine gamma something, this part. So is it okay? So we need gamma. If we consider multi-represented spaces. Okay, so anyway, so okay, so this green x tilde depends on green x, and green y tilde depends on both green x and y, and the blue x tilde depends on green x and blue x, and so on. So yeah, of course, the dependency, they are quite complicated. Okay, so but yeah, so now we have this game. So, but yeah, this game is also a bit hard to understand in that the dependencies are somewhat complicated. So to make the dependencies easier to understand, let's decompose a proponent into two players. Here, the opponent is named Marin here, and proponent is decomposed into two players, Asa and Nimue. So the names Mari and Asa come from the Mari-Asa protocol in computational complexity theory. So in the context of computational complexity theory, so Mari is a player with some kind of transcendental computational power, and Asa is the player with only feasible computational power. So in our case, Mari can do any uncomputable things, non-computable things, but Asa can only do computable things. So in our game, however, there is another player, Nimue, who also has transcendental computational abilities. So anyway, so opponent is now named Mari, and the proponent is now broken down into two players, Asa and Nimue. So Asa can only see names and cannot see points. And while Mari and Nimue can see both names and points. So green symbols are names and blue symbols are points. So green symbols are names which Asa can see, and blue symbols are points which Asa cannot see. So, and all of Nimue's moves are points, and all Asa's moves are names. So Asa can only see the name, and moreover can only perform computable procedures. Yeah, actually, so computability is a concept that can only be considered on names. So it makes no sense to consider whether or not something other than Asa is computable. So yeah, so but Asa only looks at names, so we can consider computability. Anyway, Weihrauch reducibility on multi-represented spaces can be treated as a three-player game in this way. So this way of looking at it makes it easier to discuss various arguments. Well, it may be difficult to get an idea of it. So let's take a look at some concrete examples. Okay, so this is a concrete example. So first, we want to consider non-trivial examples. So we consider a multi-represented space that is not a represented space. So for as a multi-represented space, so we consider a double negation space. So double negation representation. So what is a double negation representation? So it is something like this. So for a set X, the underlying set of the double negation of X is X itself. But the representation will be changed. So underlying set is same as X, but everything is a name of any point. I mean, any infinite sequence is a name of any point. So it is a space whose names are almost meaningless. So everything is a name of everything. So, but let's call this a double negation space. And it's a space where anything can be a name. Okay, so as an example, let's consider double negation elimination on the natural number. So which is a function that reduces the double negation of the natural numbers to the natural numbers object. So then what kind of function is Weihrauch reducible to double negation elimination on the natural numbers? The answer is that this corresponds to non-uniform computability. Non-uniform computability means that given any input, there exists a solution that is computable relative to input. So this is the meaning of non-uniform computability. Okay, so as an exercise of constructing Weihrauch reduction on multi-represented space, let's try to right to left proof. So assume that F is non-uniformly computable. So this means that so there exists an index is computing Y from X. So we assume this. So this Y can be written as phi EX, but of course E depends on X. So Okay, so now we consider this game. First, Martin creates an input of X and its name, green X. But this is Bell space. So the type of the input is Bell space. So the name and the point are the same thing. But let's be a bit explicit about both. So Martin presents both the name X and the input X. Asa has to do something about it. But since the type of input for the double negation elimination on the natural numbers is the double negation of the natural numbers, so a name of the input is meaningless. So it doesn't matter what Asa's move is. So we write star here. So any name is okay as Asa's move. Then Nime picks a point whose name is star. But since star is the name of any point, because it's a double negation space, so Nime can choose anything. So Nime takes E. This E is a witness of Turing reduction. So a witness of Turing reduction from Y to X. And let this to be a query. Then Martin needs to return a solution of IDE, but this is ID, identity function. So the solution of IDE is E. And the output side is just a space of natural numbers. The name of E is essentially E. Yeah, maybe different from E, but yeah, almost the same as E. Okay, so Martin's move is something like this. The solution E and its name E. On the input side, it was the, yeah, and then, so this is a Bell space. So, okay, so, yeah, so this was a double negation space, but on the output side, the double negation is eliminated. So a name has information. So this is a point. Asa can look at names and make some moves based on the information on names, but the names he can see now are X and E. Here note that there are many X and E's in this game, inside this game, but Asa can only see the green X and green E. Asa is not looking at the blue X and blue E. So for example, Asa does not see blue E when Nime chooses E. It is only when Martin presents the name green E that Asa is able to see the information on E. So this allows Asa to return phi X using the information on X and E. So since the type of this data is Bell space, the name phi X uniquely determines the point phi X. And from the choice of E, this is a solution to f of X. So this is because this is Y. So and Y, so this is the assumption. So Y is in f of X. So this is a procedure for reducing f to the double negation elimination of the natural numbers. So one point to make is that since Nime's play does not require computability, the procedure to give E from X need not be computable. This is a reason for the non-uniformity. Okay, so this is an example of reduction on multi-represented spaces. Okay, so the double negation space can also be used to treat various variants of Weihrauch reduction in a unified manner. Some examples are computable reducibility, omniscient reducibility.
A question in the chat.
Okay, so Asa, how does Asa know P? So if Asa do not know phi, then Asa cannot put the phi X as the next move. But now, so Asa can read this green X and green E. So Asa can use these green informations. Asa cannot use blue informations. So Martin always put so returns some green information and blue informations. So green part is a name and blue part is a name. And so now, so Martin gave Arthur these green informations, X and E. So Arthur can use these green informations, X and E. So by using these information, Arthur can create phi X. Is it okay? Okay. So, okay, so by using the double negation space, so we can characterize several Weihrauch-like reducibilities. So computable reducibility, omniscience, Weihrauch reducibility, omniscience, computable reducibility. So yeah, so I don't explain the definitions of these reducibilities, but yeah, these can be characterized in this way. So using double negation elimination, I write. So double negation elimination on X is the identity function from the double negation of X to X. So then, so we can characterize these reducibilities using double negation eliminations. But one point is, so here the definition of compositional product needs to be extended to multi-represented spaces appropriately. But it can be defined using winning strategy for a game that ends in a short round. So yeah, it's possible to define this compositional product. But yeah, I don't explain the details. Okay, anyway, so we can characterize several variants of Weihrauch reducibility using double negation space. Okay, so for a few more examples, so for example, we can also consider this kind of space. So the space of the sets of positive measure in control space, or more precisely, it's double negation space. So the choice and consider the choice function for this. So choice is a function that chooses an element of a given positive measure set. So choice is a multi-valued function, and the input is a set of positive measure, but we don't have a name. So any name, so a name is a trivial information, and then choice needs to return a point in this set A. Okay, so then, so one can show that a multi-valued function is Weihrauch reducible to this choice function on positive measure space, double negation positive measure space, if and only if F is computable with random advice in the sense of Vasco and Arno, which is introduced in 2010. So yeah, this means that there exists a computable function such that for any input X of F, there exists a positive measure set A. So F can be simulated by phi if some suitable random parameter is feeded into phi. So yeah, so this is a, so yeah, so for example, we can characterize the notion of computability with random advice using this kind of choice function on double negation space. And the proof is almost the same as before. So yeah, but I don't have enough time, so I skip. But the argument is almost the same. Okay, so Weihrauch reduction on a multi-represented space proceeds in this way. Okay, so yeah, so this is also an example, but yeah, well, let's skip this one. So I think I don't have enough time to talk about all the technical details. Okay, so now, as I said at the beginning, there are many definitions of Weihrauch reducibility on multi-represented spaces. The definition given in the previous slides is only one definition and actually corresponds to the definition given by Andre Bauer. So Andre Bauer dealt with a type of function called a predicate on a multi-represented space. A predicate is a multi-valued function such that the codomain is Bell space. So, so in fact, it's no problem to restrict Weihrauch reducibility on multi-represented spaces to functions whose codomain is Bell space. Because we can see this function f by changing the output value to names of the value. Then this is the Weihrauch equivalent to f. So by this reason, the codomain can be always Bell space. And another Weihrauch called the Bell space valid function, Bell space valid marriage function, a predicate, and introduced a reducibility notion for predicates called extended Weihrauch reducibility. Yeah, actually, Andrew Bauer introduced a more general concept which he called instance reducibility, and extended Weihrauch reducibility is a special case. Andrew Bauer's definition looks quite different from our game-like definition at first glance, but a closer look reveals that they are in agreement. So our definition agrees with Andrew Bauer's definition, one of the three definitions of Weihrauch reducibility on multi-represented spaces. Now let's also take a moment to discuss the other two definitions by Schroeder. Okay, so there are two Schroeder's definitions, one of which I will explain, which Schroeder called RW reducibility. Okay, so the definition of RW reducibility can be explained using a game, which looks roughly like this. So now opponent and proponent each split into two players. One is the name player, two name players, and 2 point players. So name player can only see names, and other point players can see points. So in the previous game, opponent was 1 player and proponent was 2 players for a total of 3 players. But in the case of Schroeder's RW reducibility, both opponent and proponent are split into 2 players each, making it 4-player games. The players op name and pro name can only see names. They cannot see points. The players of point and pro point can see both names and points. So since opponent and proponent are symmetrical, so this seems a very natural definition. However, there is one asymmetric part where only the pro name needs to make a computable move, and the other players can make any move. Okay, so Schroeder's RW reducibility is defined in this way, and I think we will agree that it's very natural. But let's look at the properties of this RW reducibility. So since opponent is weaker than the previous definition, so the proponent side is more likely to win. In other words, if F is Weihrauch reducible to G, then F is RW reducible to G. However, this RW reducibility is too easy to win because opponent is too weak. So for example, any function can be RW reducible to the W negation elimination on the natural numbers. So the situation is quite different from the previous one. So in addition to RW reducibility, Schroeder also introduced the AW reducibility, but the definition of AW reducibility is unintuitive and a bit complicated. So I'm not sure of the exact strengths, but it seems relatively close to our Weihrauch reducibility. But at this time, I'm not sure if they are the same or not. Okay, anyway, so in summary, so while Schroeder's RW reducibility is fairly natural, opponent is too weak, and so this reducibility is not useful for analyzing double negation type predicates. So in fact, it's almost it's almost the same as the ordinary Weihrauch reducibility, and I suspect that there is not much new to be found in it. So the definition of AW reducibility is complicated, so I'll skip it for now. Now going back to the first definition of Weihrauch reducibility, so equivalent to Bauer's extended Weihrauch reducibility. So it may seem a bit odd to have one opponent and two proponents, but there are many advantages to considering this definition. As we have seen, the main advantage is that it allows us to analyze double negation type problems such as non-uniform computability and advanced computability. There is an even bigger reason. In fact, the first definition of Weihrauch reducibility on multi-represented spaces has a lot of natural characterizations. This is an advantage. I'd like to explain this. Okay, so to explain this, now to think about Weihrauch reducibility is to think about computability relative to certain kind of oracle. So which is to think about a universal machine relative to such oracle. Okay, so let's first recall what a universal machine is. So a universal, for example, a universal Turing machine is a machine that could simulate the computation of any Turing machine by taking its code as input. So formally, so for any computable function, so if we take a code of this function EF, then so you can simulate this F if we feed EF, the code of F, to the machine U. So this is a property of universal Turing machine. So of course, this notion can be made relative to any oracle. So a universal machine for alpha relative computation is something like this. So for any alpha computable function, if we take alpha relative code EF of F, and if we feed EF to this universal machine, then this can simulate F alpha. So this is a property of a universal Turing machine relative to an oracle alpha. So U alpha can simulate any alpha computable function. Okay, so here alpha relative computability can be replaced by U alpha relative computability. Yeah, because alpha relative Turing machine is also alpha computable. So the alpha computable function F alpha can be expressed as a composition of a computable function F and universal machine, alpha relative universal machine U alpha. So this can be rewritten as this. For any computable function F, there exists a code EF such that for any n, U alpha EFN is equal to the composition of F and U alpha of n. Okay, so we write F tilde for the function that outputs EF, the pair EFN for input n. Then the property of this equality can be expressed in this simple form. U alpha composition F tilde is equal to F composition U alpha. Okay, so let's declare this formula to be a property of the abstract alpha relative universal machine. So for any computable F, there exists a computable F tilde. U composition F tilde is equal to F composition U. Okay, so this is a property of the abstract universal oracle computation. The continuous version of this property seems to be called transparent these days in the computable analysis community. So a partial map on we consider continuous Bell space version of this notion. a partial function u on Bell space is transparent if for any continuous function on Bell space, there exists a continuous function f tilde on Bell space, u composition f tilde is equal to f composition u. And if such a transformation from f to f tilde is computable, we say that u is computably transparent. Yeah, in the case of the Oracle computation in the previous example, it's actually possible to effectively find the code of f tilde from a given code of f. So we call such a map computably transparent. And now we move our attention to multi-valued functions. It's also important to consider multi-valued function. So the notion of universal computation or transparency can also be introduced for multi-valued functions. The definition is almost the same as for single-valued function. The only difference is that the equality relation here has been changed to refinement relation. Here, refinement relation means that if f and g are multi-valued function, then we say that f refines g if f of x is a subset of g of x. I mean, so if gx is defined, then fx is also defined and is a subset of gx. So in this case, we say that f refines g and write like this. So a partial multi-valued map is transparent if for any continuous function f, there exists a continuous function f tilde, u composition f tilde refines f tilde u, f composition u. And if such transformation from f to f tilde is computable, then we say that u is computably transparent. Okay, so this is the definition of computable transparency for multi-valued functions. Okay, so next we will discuss a generalization of many-one reducibility. So many-one reducibility is usually defined for subsets of the natural numbers, like this. So, but considering a characteristic function instead of a subset, then the definition of many-one reducibility can be written as this. So there exists a computable function phi on natural numbers. The characteristic function of A is equal to the composition of the characteristic function of B and phi. So yeah, phi is a kind of inner reduction. So many-one reducibility is something, some kind of reduction which only has an inner reduction. So using this idea, we can generalize many-one reducibility to any function. So first, many-one reducibility for single-valued function on Bell space is defined by precomposition by computable function. And in the case of a multi-valued function, this equality is replaced by refinement relation. So yeah, in other words, many-one reducibility for multi-valued function on Bell space is defined by a refinement of a precomposition by a computable function. So f is many-one reducible to g if there exists a computable function phi on Bell space. The composition of g and phi refines f. So this is a definition of many-one reduction for multi-valued function. Okay, so we have said that computable transparency is an abstraction of universal Oracle machine. So using this many-one reducibility, let's look a little further at the connection between computable transparency and universal Oracle machine. Now let's write func for the set of all multi-valued functions on Bell space and func ct for the set of all computably transparent multi-valued functions on Bell space. So since func ct is a subset of func, there exists an inclusion map from func CT to func. Assuming now that they are preordered by many one reducibility, then the inclusion map has a left adjoint in this. I mean, left adjoint means this formula. I mean, for any computably transparent map G, F is many one reducible to G if and only if via F is many one reducible to G. And be careful that via F is always computably transparent because via is a map from func to func CT. So via F is a computably transparent function. So yeah, roughly speaking, so this left adjoint via is an operator that generates a minimal computably transparent function from a given function. Minimal with respect to many one reducibility. I mean, so roughly speaking, this via is a computably transparent function generator or something like this. Okay, so now let me explain why I named this computably transparent function generator via. So interestingly, this left adjoint can be thought of as the operation to create a universal Weihrauch machine relative to a given oracle. So a universal Weihrauch machine is like a Weihrauch version of a universal Turing machine. So our claim is that computable transparency was in fact a complete characterization of the universal Weihrauch oracle machine. I mean, in this sense. So yeah, via is left adjoint to the inclusion map. And so the point is that using this via, we can recover a Weihrauch reducibility in this sense. So we can show that F is Weihrauch reducible to G if and only if F is many one reducible to via G, where via is any left adjoint of the inclusion. So via is any left adjoint, so it does not mean anything. So the point is that via is just the name of a computable transparent function generator, which a priori has nothing to do with Weihrauch reducibility. Nevertheless, the Weihrauch reducibility can be recovered from this via computably transparent function generator. The point is that this via has no meaning a priori except that it is a left adjoint of the inclusion. And it's just something derived by mathematical operations. The via derived by this mathematical manipulation somehow automatically recovers Weihrauch reducibility. So we can consider the left adjoint of the inclusion as a universal Weihrauch machine. And using this, we can show that the Weihrauch degrees of multi-valued functions and the many one degrees of computably transparent maps are isomorphic. Here at this stage, we are still talking about a Bell space or represented space, but we are not talking about a multi-represented space yet. Anyway, Weihrauch reducibility is something that automatically appears when we have the notion of computable transparency and the notion of many one reducibility. So in fact, there is no need to define Weihrauch reducibility. Now let's extend this idea to multi-represented space. And so I don't have enough time, so I don't explain the definition, but we can extend the definition of computable transparency and many one reducibility to any multi-represented space. And then we can show the same thing as before. So consider the set of all partial multi-valued functions of multi-represented space, func M leap, and then consider computably transparent ones in func M leap. So func CT is a subset of func, so there is an inclusion. So the inclusion from func CT to func has a left adjoint E via, and so yeah, left adjoint means this. And then by the same argument, so we can recover a Weihrauch reducibility of multi-represented space by using this left adjoint. So I mean, so F is Weihrauch reducibility to G in this. So, but F and G are multi-valued function on multi-represented spaces. If and only if F is many-one reducible to E via G, where E via is any left adjoint of the inclusion. So then we can show that the Weihrauch degrees of multi-valued function on multi-represented spaces is isomorphic to the many-one degrees of computably transparent multi-valued functions on multi-represented spaces. Okay, and also, yeah, yet another characterizations. So yeah, there are a lot of characterization of Weihrauch reducibility of multi-represented spaces. So, for example, so we consider truth values. So we now consider subsets of Bell space or mass problems, and we consider mass problems as truth values. So yeah, a subset of Bell space can be thought of as a truth values if we consider a clean realizability interpretation. Then, so then in this case, let's consider monotone map on truth values. So we say that a function on truth values is monotone if for any mass problems, for any truth values P and Q, P implies Q implies JP implies JQ is realizable. So this means that for any mass problems P and Q, there exists a computable function such that given a code for a continuous function that transfers an element of P to an element of Q, returns a code for a continuous function that transfers an element of JP to an element of JQ. Here, the computable function does not depend on P or Q. So this is the definition of monotonicity. Okay, so now let's introduce a preorder on these monotone functions. So we say that J is less than or equal to K if for any truth value P, JP implies KP is realizable. So this means that there exists a computable function that transfers an element of JP to an element of KP. And that computable function does not depend on P. So we call this order realizability order. So it's a very simple definition. There is no represented space or anything like that. There is only Bell space. So this is a, okay, so yes. Okay, so it's a very simple definition. So, but yeah. So, okay, so yeah, this is the main theorem. So, okay, so this is a final theorem in this talk. So the realizability ordering on monotone function is very simple and a natural concept. So I think, so we can show that the Weihrauch degrees of multi-valued function on multi-represented space is isomorphic to the realizability degree of monotone functions on truth values. So, but this is only when we consider multi-represented spaces. So if we just consider represented spaces, so the Weihrauch degrees on represented spaces is just the realizability degrees of intersection preserving monotone functions on truth values. So if we want to consider all monotone functions, we need Weihrauch reducibility on multi-represented spaces. Okay, so that's all. Okay, so this is the references. So thank you very much for your kind attentions.
Thank you, Takayuki. Any time for a quick question? Any questions? Guess not. Oh, yep. One from Elvira.
Since you mentioned these Arthur Merlin games, I didn't it wasn't clear to me. So do you kind of bound the number of interactions, or any finite number is fine?
So okay, so you mean this game? Okay, so
Yeah, I mean, in each of your, I mean, for instance, when you, in the
Okay, so-
Weihrauch game, which, so the number of interactions is unbounded. It can be any number.
yeah, can be any numbers. So at each round, Asa need to pick the symbol query or hold. So if Asa pick the symbol query, then the game continues. But if Asa pick the hold, then this means the game holds. So so the number of rounds are determined by Asa's strategy.
Mhm. Yeah, okay. Yes, just curious because, you know, in these complexity games, the number of interactions is one of the key parameters. So I
Mhm.
wonder if
Yeah, yes.
could somehow restrict this, I don't know exactly, in relation maybe to the functions or something, so that it's not completely, I mean, it cannot be any n, but okay. Thank you.
Okay, sorry. So in the case of this usual Weihrauch, I mean, so sorry, this is a generative version. So I mean, in the case of the usual Weihrauch reducibility, in the case of usual Weihrauch reducibility, the game ends at this round. So, sorry. So there are several definitions of Weihrauch reductions, and so this Turing Weihrauch game is a bit different version of Weihrauch reducibility. So, so in the case of the first Weihrauch reducibility, so the game ends at the fixed round. So this is actually, so the game only consists of 4 steps. But
Thank
yeah,
you.
there's sorry.
A viewer says thank you. I think we need to go on to the next talk now. Thanks so much, Takayuki. Let's thank Takayuki again.